Okay, so in this exercise, we're asked to prove the regularity of this append1 language operation. That is, if we have a regular language L and we apply the operation append1 to it, then the resulting language that comes out of that is also regular. Okay, and so what does append1 actually do? It's a language operation that takes each string in L, right? So from the set builder notation, each of the strings in L have a 1 appended to it, right? And so here, a 1 is a letter because our alphabet is assumed to be over 0, 1. Okay, so what's a quick example? We just look at a quick example. Suppose L is the language that contains 0, 0 and 0, 0, 1. Okay, then if we apply append 1 to the language L, then the resulting language we'll get will be each of the strings in L, so 0, 0, and then 0, 0, 1, with a 1 appended to the end of each of the strings, right? So you'll have a 1 appended to 0, 0, and a 1 appended to 0, 0, 1. Okay? And so this resulting language is what comes out of applying the operation append1 to L. Okay? And so intuitively, it does seem like this should preserve the regularity of a language, because it'd be quite weird if appending a single letter to each of the strings in a language that's regular could somehow make it not regular, right? Because if you have a machine that accepts all of the strings in L, then you can just extend that machine by one additional transition, where that transition is a 1, and then you'd have a machine that accepts append1L, right? And that's exactly the proof by construction that you could give, right? So there are two main ways of proving this statement, I think. The first one is by construction. So if we assume that L is regular, then there must exist, by definition, a DFA M such that the language accepted by M is L, right? Then to create, right, then to create an FA M prime such that the language accepted by M prime is append 1L, you need to do exactly what I just said, right? So you would take the machine M, okay, so this is the machine M that accepts the language L, and then for each of the strings that are accepted by this machine M, so that is that belong to L, right? So suppose you have this string that's accepted by M and this string that's accepted by M, right? Meaning that they're also in L, okay? Then for each of these strings, you force the bigger machine M prime, which you're creating, you force the bigger machine M prime to require an additional transition of a 1. And this additional transition simulates the actual appending of the letter 1 to each of the strings in L, right? So then you would have to add an extra transition 1 for each of the final states, right? So for each of the final states, you would say, for each of the final states in M, have an additional transition where you have a 1 that goes out of the machine into another final transition, another final state, sorry. And so because you don't want to allow the strings W1, the string only W1 to be accepted, right? You want W1 concat O1 to be accepted. Then what you want to do is you want to remove these final states from the machine M prime, right? And just keep them as regular states, okay? And so what this does is that this forces any string accepted by M prime to end with a 1. And because what you're doing is you're passing each of the strings through M first, right? M filters out all the strings so that you're only accepting strings that are L already. And then this additional transition, right? These additional transitions force each of the strings to have a 1 appended to them, right? So you could formalize this. You could exactly assign each of the elements of the tuple M prime, okay? But I won't go into too much detail because there's actually a what I think is more elegant way of proving this, okay? And so that's by noticing that append1 L can be rewritten as a language operation that we already know is closed, that we already know regular languages are closed under. And that language operation is the concatenation. So what you need to notice is that if you have append1 L, then this is actually equivalent to taking the language L and then concatenating this. So this is the language concatenation. So concatenating L to the language containing the letter 1, right? So this is the language containing only 1. And so this is true by definition, right? So this is true by definition of language concatenation. And now, because L is regular, okay, so because L is regular and the language containing 1 is regular, why is this regular? Because namely, it's a finite language, right? And finite languages are always regular. Or you could also just construct an NFA, right? You could construct, if I write it on the side, you could construct an NFA. This would be the NFA that accepts the language containing just the letter 1, right? So 2 reasons why this is regular then, okay? And so because L is regular and this other language containing a single letter is regular, then by the closure properties, L language concat, the language containing 1 is also regular. And so therefore, append 1L is regular. Okay, so you could have done this either by construction or by noticing that you can rewrite this as a set of language operations, right? Or essentially as an application of a language operation, okay?